Hello Year 12 and welcome to our second video for vectors. In the first video we learned what a vector was. It describes a magnitude and a direction. And now we're going to look at it says components and column vectors, but really we're looking at lots of little bits to do with vectors. Okay, so to begin with, let's talk about a position vector. Now we can express vectors in lots of different ways. I can do it like this. This means the vector from the origin to A. Or I can write it like this. Which tells me it's from the origin to the coordinates AB. So I can write it like this, or I can write it like this as well, and I can write them other ways. Right? How exciting. Not necessarily difficult, just a lot of detail. So, here we're going to express each of these vectors in component form as an ordered pair and in a column vector notation. So in component form, what I'm really doing is describing how far across and how far up they go. Now to do that, right, I'm going to sort of attach to those magnitudes, direction in the form of these special little vectors I and j. So I means units to the right, if you like, and j is units up in terms of the number plane. Okay, I'll show you what that looks like in a moment. An ordered pair, just the same as coordinates on a number plane, and for that very reason tend to avoid them, or certainly I'm going to avoid them as much as I can when we're describing vectors, because, well, they just look like coordinates and I need to express these as vectors. Sometimes that's done by using sort of pointy brackets, but no, we've got enough other ways to express vectors, so I'm going to avoid that one. Now a column vector, sort of like coordinates in brackets, except instead of side by side it's top and bottom, where the top one is like the x part component and the lower number is the y component. It does come in handy when we learn some other maths somewhere else down the track, when we learn about matrices and the like. But easier to recognize a column vector as a vector, and I think in component form is very helpful, very sort of convenient form as well. So here we go. A goes across 2 and up 1. So in component form that's 2i, that's across 2, right? 2i, and up 1, so plus 1j. I can leave the 1 out. Okay, so there we go. A is 2i plus j in component form. As an ordered pair it is, of course, 2, 1. And in a column vector, as a column vector, right, 2, 1. The x coordinate on top, the y coordinate underneath. They can be with these square brackets or with curved brackets. So many ways, really. Not necessary, really, to use all of them all the time. This will do us, but we've been asked to do it for this question. Now, B. You can see it goes across 2. Now, that means I've got 2i, but no j, so I'm just going to write it as 2i. Right? The vector B is 2i. Now, as an ordered pair, right, that vector might finish at 2, 2, but that's not where it's gone. It's gone 2 across, that's true, but it's gone up 0 from this start point. So, as an ordered pair, it's 2, 0. That's what the vector B looks like. And the column vector, 2 over 0, like that. Righto, third one, C. It goes back 1, so that's negative I. And down 3, so negative I minus 3j, which we can also write as this, negative 1, negative 3, or like this. Okay, that's component form, ordered pair, and column vector notation. All different ways to say the same thing. Now, we have these vectors here. We're asked to draw them on the number plane. Then I want to express PQ in terms of OP and OQ. Well, here's my number plane. And OP, 2, 2, go across 2, up 2. OQ, over the origin, remember, is across 3, down 1, across 3, down 1. Boom, there we go, excellent. Now, PQ, I can draw it up from P to Q. You can rearrange these things, but I want to write PQ in terms of OP and OQ. Well, consider this, right? Let's move that vector, PQ, now back to the origin. Now, using P and Q, how do I get from the origin down to this point here? Well, what I do is I start off doing Q and then I do negative P just the same as if I want to go from, I don't know, 3 to 7 on a number line, right? I do 7 minus 3 tells me how far to go. I've got to go 4 further to the right after 3. So, to get from P to Q, I do OQ minus OP. Right, so that's OQ, and then I subtract, right, remember that's like going the opposite direction, subtract OP, and then tip to tail, that is the vector PQ. Rightio, PQ. All good? Wonderful. So, PQ is equal to OQ minus PQ. No, minus OP. Typo there. Change that. Okay. PQ equals OQ minus OP. Rightio, moving along. We've got to simplify these in different forms and then show the results graphically. So they are all the same operations here. 2i plus 4j, that's component form, plus 3i minus 2j. So it's the 2 plus the 3 equals 5i. And 4 minus negative 2 is, 4 plus negative 2. 4 minus 2 is 2j. So 5i plus 2j. Alternatively, it's 2 plus 3 is 5. 4 minus 2 is 2. Right, 5, 2. And 2 plus 3 is 5. 4 minus 2 is 2. Rightio. There we go. Each of the three forms. I want to show that graphically. So here's number plane again. Let's get my head out, right? Hey. Now, 2i plus 4j. 2i plus 4j. Should be up here. Should be. Here it is. There it is. 2i plus 4j. Now, 3i minus 2j. 3i minus 2j should be down here. I don't want to add those together, so I'm going to take this one. Whoop, tip to tail. Look at that. That is magic. And now, the resultant, from the origin up to that tip there. And we can see that's across 5 up 2, right? 5i plus 2j. Wonderful. Right, just as we predicted. 5i plus 2j. Okay, there's more and more examples. The magnitude of a vector, how long it is, how big it is, we can find that using Pythagoras' theorem, because really we're going across and up. They're at right angles to each other, our x and y coordinates, or x and y directions. So, if my vector u is expressed as xy, then right, we do these straight brackets, sort of like absolute value, which is also telling us magnitude. Right, these straight brackets, that means magnitude, and this is just a scalar quantity, it no longer has direction, is the square root of x squared plus y squared. Okay. So we've got some examples here. Find the magnitude of these vectors. The magnitude of v is the square root of negative 3 squared plus 4 squared, which is of course 9 plus 16 adds to 25. The square root of 25 is 5. Now we could say plus or minus 5, but magnitude, no direction, okay, only the positive answer. Similarly, the magnitude of u is the square root of 2 squared plus 7 squared, which is square root of 53. Okay, square root of 53. Am I going to do anything with that? Nope. That's it. That's the magnitude of u. That's finding the magnitude. That's been pretty helpful, I think. Now, the exact magnitude of AB if OA is 1, 2, and OB is 3, negative 2. So what I need to do here, apart from scratch my nose, is find the vector AB, first of all, which is OB minus OA. So 3 minus 1 and negative 2 minus 2. Right, gives me the vector 2, negative 4. That's what AB is. That's the vector. But I want the magnitude of 2, negative 4. So the square root of 2 squared plus negative 4 squared is root 20, which we might write as 2 root 5. That's one of them. Here's another one. Negative 6, negative 5, and negative 4, 3. So I want to go AB, that's B minus A. So negative 4 minus negative 6, that's like negative 4 plus 6, or 6 minus 4 is 2. Negative 5 minus 3, right, so it's going to be 2, 8. Right, that is our vector AB. Now this time, yeah, I guess we're column vector here and ordered pair here. So I'm sticking with the ordered pair this time. Anyway, now to find the magnitude of AB, we are going to do the square root of 2 squared plus 8 squared, which is root 68, which is, right, 4 lots of 17, 2 root 17. Okay, magnitude. That's been a helpful thing. We've learned something there. Moving along now, unit vectors. A unit vector is just a vector that is 1 unit, has a magnitude of 1 unit long. Same direction, but just 1 unit long. We can sort of almost treat that as though a special vector that just describes direction in a lot of ways. We put a little hat on top of it to show that it's a unit vector, and we call it u hat. There you go, u hat. There are worse things to be called than hat, I guess. Anyway, here we go. That's the vector u with a magnitude of, well, that. But the unit vector is just 1 unit long, right? Same direction, but just a magnitude of 1. How do we find that? Well, we take our vector and we divide it by the magnitude, right, like this. So our unit vector u hat is our unit vector u over the magnitude of u. There we go. Here we go. Let's try this out. Show that this is a unit vector. How are we going to do that? We're going to do it like this. We're going to find the magnitude of that and demonstrate that's equal to 1, which makes it a unit vector. To find the magnitude, square them, add them together, take the square root. 1 over root 2 squared is half. Half plus a half equals 1. Square root of 1 is just 1. So therefore, u is a unit vector. Not you are a unit vector. U is a unit vector in this case. Okay, moving along. We're nearly there. A vector parallel to this that has a magnitude of 5. So I need the same direction, but I'm not after the unit vector. Well, not per se, not at the end. Magnitude of 5. So what I'm going to do, and there could be other ways to do this, I suppose, but I'm going to go through it this way. We are first going to find the magnitude of u, like this. Okay, 3 squared plus 2 squared, root 13. Now I'm going to find the unit vector. I'm going to find u hat. I'm not going to find your hat. So, instead of 3, 2, it's 3 over root 13, 2 over root 13. I have switched to this component form now because, I don't know, fancy fractions as column vectors get a bit annoying. Okay, so I find this to be a bit better. So that's u hat. Finally, I take u hat and I multiply it by 5. So, remembering this has a magnitude of 1, if I multiply it by 5, it'll have a magnitude of 5. So there we go. 15 over root 13i plus 10 over root 13j. I could check that that still has a magnitude of 5 by finding the magnitude of that, but well, I'm not going to. You can check it out if you like. Anyway, that's it for now. That's it for components and column vectors. There's a lot more than that in there, though. What was in there? Well, here we go. If a has the point 5, negative 2, then OA is 5, negative 2, or we could write like this column vector, or in component form like this. That's something. Also, the vector AB is OB minus OA. That's helpful too. The magnitude of u, and that's what that notation refers to, the magnitude of u is the square root of x squared plus y squared. The unit vector, u hat, can be found by dividing our vector by its magnitude. Okay, that's it. That's it. There's a fair bit there. If I got anything wrong, and I probably did, or maybe you just really enjoyed those bad puns along the way, feel free to let me know. Ask me a question. Otherwise, I will see you in the next video, which is about the dot product. Okay, enjoy.